Moving on to Unit 4.3 of the WJAC course, we move on to alcohols and phenols. So we're actually going to start off with a recap from Unit 2, which is the formation of your aliphatic alcohols from a halogen alkane. Now this is caused by nucleophilic substitution, so this is bion nucleophile, which is an electron-rich species. And this is just on to our normal aliphatic halogen alkane. Now this is done due to our differences in electronegativity, and of course with our nucleophile, which would be OH minus in this case, will be attracted to this positive, and this will push that bond towards there, causing our OH carry on like that. Okay, so from our Unit 2 knowledge, we know the difference between a primary, secondary, and tertiary alcohol. Primary alcohol is when it's usually a terminal to the chain, so it's usually at the end, and it's an OH which is attached to one carbon, which is attached to a carbon which is attached to one other carbon. With our secondary alcohols, we have a within the molecule hydroxy group. So this is when the OH is attached to a carbon which is attached to two other carbons. And then moving on to our tertiary, which is our final kind, is when we have an OH attached to a carbon, which is attached to three others. So that is our tertiary alcohol. Now, we also know from Unit 2 the oxidation of these. So we know that a primary alcohol will oxidize into an aldehyde, and then finally onto a carboxylic acid. Now, this will happen with acidified Cr2O7 which is acidified potassium dichromate, but I got rid of potassium, so it's just acidified dichromate. And then we know that this will also undergo it, and it will form a ketone, and no further reaction will occur. And our tertiary alcohol is too stable, so we'll have no reaction with acidified dichromate. So that's our basics, Unit 2. We know that our reducing agent will be written as, in terms of hydrogen. That's reducing agent, sorry. Our oxidizing agent is in terms of oxygen. So it has an O in the middle. Okay. So that's the start. And now we're going to move on to a new thing. So we're moving on to now the reduction of our carbonyls to form our alcohols. See, from our carbonyl, we know we got aldehydes. So this is our C to bond OH to an R. This, under a reducing agent, which can be written as square brackets H, will go to a primary alcohol. And reducing agents are in terms of addition of hydrogen and loss of oxygen. And a ketone will go to a secondary alcohol. That is reduction. So we can form alcohols we've just discovered from carbonyls. That's another production method of an alcohol. Okay, so now moving on, we want to react alcohols with halogen to hydrogen halides to produce chloroalkanes. Now this is a hard process then from our producing alcohols from halogen alkane, because from that we have our usual that. However, this bond here, due to a bigger difference in electron, we see this is a stronger bond, so it's a hard process in order to produce, let's say, a chloroalkane from an alcohol than it is to produce an alcohol from a chloromethane. So, to the production of a chloroalkane from an alcohol, this requires HCl and anhydrous or dry zinc chloride. Now, an example of this would be butan-2-ol will form 2-chlorobutane if reacted with the correct reactants. Now, if you want to produce a bromoalkane, you're going to use KBr and H2SO4. That is conc sulfuric acid. So another example of this would be our propan 1-ol, which would be a primary alcohol. Oh yeah, sorry, this is a secondary alcohol, and this is a primary alcohol. And this is going to form our 1-bromobutane, 1-bromopropane. So that's the production of chloralkanes, halogen alkanes from alcohol. So now we're going on to, which is also a small recap from Unit 2 as well, is our production of an ester, which is an addition-elimination reaction, or condensation reaction, which is the loss of a small molecule. In this case, with an alcohol and a carboxylic acid, it's the loss of water. So, our normal alcohol, and so I'll draw it like this: R to OH plus our normal carboxylic acid is going to form our ester. Oh, it's going to be horrible to draw now. I'll do a proper molecule. We'll form an ester. And our ester bond, of course, is C. That is an ester bond. So if I do methanol, which is C to OH, like that, plus ethanoic acid, which is normal vinegar, we are going to form, now the conditions of course are concentrated sulfuric acid and heat. So we're going to lose, this hydrogen here is going to be lost, and the OH from the carboxylic acid group are going to be lost. And this is due to an experiment which they'd labelled individual ones with oxygen 18 to see which molecule the OH was lost from, and they found that the OH from the carboxylic acid is the one that's lost. Now, this will form this ester. So this ester is known as methyl ethanoate. A way to remember naming these is that the "-ile" comes from the alcohol and the "-08" comes from the carboxylic acid. So another way for us to make an ester from an alcohol is to do an alcohol plus an acid chloride. So I'll call it ethynyl chloride as an example. Ethynyl chloride for this experiment. Now, due to the reactivity of ethynyl chloride, there's no catalyst needed or conditions. This is just due to the complete reactivity of ethynyl chloride. It will still form an ester. It's still a condensation reaction. It's still an addition elimination reaction. But in this case, instead of water being lost, we actually lose HCl. So it's a bit more violent reaction, a bit more dangerous. Now, the C to Cl bond is weaker than the C to OH bond, and this is the fundamental of the reactivity of this reaction. Acid chlorides, however, tend to be quite expensive, so different processes may be used. Okay, so now we're going to move on to phenols. So we've talked about our aliphatic alcohols. Now we're going to move on to phenols, which is, this is a phenol. So you've got a hydroxy group on your benzene ring directly attached. Now, you tend to take phenol as your priority name. So if I attached a chlorine onto here, it would be known as 2-chlorophenol. As an example. Or with nitro, if you put NO2 there, you'd have 2-nitrophenol. Okay, so this is our phenol. Now, phenol is acidic. Now, acidity, as you may or not know, is down to the stability of the anion. So when you lose your H+, you form this phenoxide ion. This phenoxide ion is slightly acidic. Okay. This molecule is also quite strong because you've got the O-, you'll have your P overlap with this, and you'll get your, as we talked about in benzene, kind of your dummy shape of the delocalized electrons. Now, in terms of phenol's acidity, we use it as a reference with the carboxylic acid is a stronger acid than a phenol, which is a stronger acid than aliphatic alcohol. The test for this is phenol will react with sodium hydroxide, but it will not react with sodium carbonate. And carboxylic acids will react with both. So that is the distinguishing test. So if you have a carboxylic acid reaction with sodium carbonate, you'll get bubbles. That is how you can tell. If there are no bubbles, with sodium carbonate, you can assume that it's a phenol without any further tests necessary for that reaction. Okay, going on to the final bit is the reactions and the tests for phenol. So phenol and bromine water. This is actually a test, which I will later discuss the two tests. So if you react phenol with bromine, so it's like the bromine water test, you will get 2,4,6-tribromophenol. That's there, like this. Sorry, I might have confused you there. It's me being silly. 2,4,6-tribromophenol. Now, if any of the 2,4,6 positions, so that's this position, this position. Sorry, it's not Br2. I don't know why I'm doing that. It's just normal Br. So if any of these 2,4,6 positions are being used up, it will be substituted with remaining Br. So if you got like a nitrophenol, your remaining. So let's say there was a nitro group on this one. That would remain a nitro group, and you'd get 1 nitro 4,6 bromophenol. And that will form a white precipitate. Your 2,4,6-tribromophenol. And your orange colour from your bromine will go to colourless. So this molecule here is a white precipitate. And that is the reaction of it with bromine. Now, phenol will react with an ethanol chloride as well, but phenol will not react with COOH. This is due to delocalization of a lone pair on the oxygen with the pi system. So usually alcohols and phenols react as nucleophiles, but due to the P overlap, this is difficult for phenol to act as a nucleophile with carboxylic acid. So an example of its reaction with an ethanol, this is going to be with ethanol chloride again. That's our phenol. It's going to form and our condensation reactions. Of course, we have a loss of a small molecule. So, But phenol chloride is usually expensive, so antimonic anhydride is used, but a base on this reaction by itself is quite slow, so you can use a base such as pyridinine to catalyze the reaction. So another test for a phenol is its reaction with iron 3 chloride. And if a phenol is positive, a phenol is present, you will get a purple positive result. So you get purple colour in your solution. That is it for Unit 4.3. I will move on to questions in the next bit.